In this video, we will introduce the normal distribution based on what we've learned from our coin tossing experiments. Let us recall the probabilities for two coin tosses. The probabilities for getting heads 0 times, so 2 tails, once, so one of each, or twice heads. And these were 1 divided by 4, because there's 4 possible patterns, 25% to get 2 heads, 25% to get 2 tails, and 50% to get 1 of each, because there's 2 ways out of 4 to get one's heads and one's tails. And as you will recall, the total of these probabilities must be 100%, or 1. Because these are all the possible outcomes. When we think about 4 tosses, these are the probabilities of getting the different number of heads indicated. So from 0 times heads, all tails in 4 tosses, to 4 times heads, going through once or twice, so twice each, or 3 times heads. And the actual numbers are these are the probabilities here in percent. And again, of course, they must sum up to 1 or 100%, because these are all the possible patterns and one of these must happen. For 10 tosses, this is what the expected frequencies look like. What about lots more tosses? Let's see what happens with 100 tosses. So these are the expected frequencies for getting from 30 through 70 times heads. We're not plotting the probabilities for getting fewer or more because they're very, very low. So if you toss a coin 100 times, then you are expected to get at least about 30 times heads and at least about 30 times tails. Larger ratios are very, very unlikely. What about 1,000 tosses? What are the expected frequencies for that? Okay, we can see a nice shape being formed here by all of these bars. And we see that the probabilities here range from about 440 to 560. Of course, you can calculate them for fewer or more times heads, but they're exceedingly low and can be ignored. So most of the outcomes will contain at least 450 of each. What about the 10,000 coin tosses? Okay, so now we are likely to get between 4,850 and 5,150. And you see that all of these little bars that correspond to individual counts are so close that they have merged into one another. So they have formed a smooth curve. If we imagine joining the tops of all these bars in each case, in the case of 10 tosses, we see that this is kind of a jagged mountain because you can see each individual bar. It's a bit smoother with 100 tosses. If you do the same thing, it's pretty smooth with 1,000. And there are no visible corners of any sort by 10,000. And indeed, the bars are merging into each other. So imagine starting from 10,000 tosses, imagine now that we go up to tossing forever. So this means that the number of tosses goes to infinite, uncountable. And the little bars in here become so thin that they actually have no width. But there's so many of them They completely merge into one another, into one big area, one big blob. The shape of the curve joining the tops of all these infinite individual bars for uncountable number of tosses is called the normal distribution. And this is what it looks like. The reason that we're introducing this as an extension of the number of tosses is because we want to retain a very important lesson from tossing coins. And that lesson is that the area under this curve is equal to 1, because that's the total probability. So we don't have individual bars here to add their heights because there's an infinite number of them and each one is infinitely thin. So you can't work with individual bars. But what you can do once they are infinite is you stop thinking about bars and adding them and think about areas. So this total area under here is the total probability of everything that can happen, which has to be 100% or 1. So the shaded area here under this curve has an area of 1. And obviously, this curve is symmetric. So whatever happens this way, exactly the same thing happens this way. Okay, so this means if I cut it in exactly half, so this is the top of the curve, if I cut it in half, and if the whole thing is equal to 1, then the left half will have to be equal to 1/2. So 50% probability. This shaded area here is equal to 0.5 or 50%. And of course, this is also 50% because it's the other half. Okay, so what about different points in the curve? The important thing about the normal distribution is that we can calculate the probability for any given point. So at the point that I have indicated with 1, what is this area? Well, it is about 84%. So the area from far left all the way up to 1 on the normal distribution is equal to 84%. And because the whole thing is 1, this means that what's left must be 100 minus 84%, which is 16%. So 84 plus 16 is 100. So if this is 16 from 1 to the end forever, and because this is a symmetric curve, then this also should be 16 from minus 1 to the left end. So 16 plus 16 means that the probability that is outside of the range from minus 1 to 1, the sum of these two areas is about 32%. And if that's 32, then what's left to complete the 100, it has to be 68. So there is a 68% probability between minus 1 and 1, and a 32% probability outside of this range. What about the range from minus 2 to 2? It turns out this is about 95%. So what's left to be outside of this range? This probability is 5%. 5 plus 95 equals 100. So a probability of 0.05 is associated with the area outside of the range minus 2 to 2. Therefore, one side only would be half of that. What is half of 5%? That is about 2.5%. That is beyond 2. on the right side, on the positive side. And what about the range between minus 2.5 and plus 2.5? This probability here is about 99%. And therefore, outside of this range, so from 2.5 and above and minus 2.5 and below, the sum of these probabilities is about 1%. And if we go all the way from minus 3 to 3, this is very hard to see, but there is a point right here. And so almost everything is included. The probability within 3, from minus 3 to 3, is 99.7. So we have some proportions that are based on the normal distribution. And I realize you are still wondering why we're doing this, but this will become clear very soon. And this is very, very important. I need you to learn these sets of numbers. Actually, you only need to learn one column. This is the easiest one because they're all related. So as we saw, if you think about 1, there is 68% from minus 1 to plus 1, which leaves 32% to be outside this range. And therefore, each half, so each tail, the right tail above 1 or the left tail below minus 1 has to be 16%. So if you remember this, 32, then you know that inside has to be what's left from 100, and each tail has to be half of it. And for 2, we have 95% within the range minus 2 to 2, 5% left for outside the range minus 2 to 2. Therefore, each tail would be 2.5%. Again, if you remember the 5, then this is what's left for 100, and this is half. And the third set of numbers to remember corresponds to 2.5. And that's because it results in the easy number of 1% outside the range, 99% within the range from minus 2.5 to plus 2.5. And therefore, each tail must be about 0.5%. Okay, now, why is this important? Why are you supposed to learn these 3 numbers? You should really memorize these numbers. Not all the others, but these 3 you should memorize because they're the basis for all comparisons and conclusions in statistics that will follow. You can actually check out a lot more different values and how they partition the probability area if you go to this link. Now, why are we so concerned, so interested in this curve? I mean, it looks nice, but it's not obvious why it's so important. The mathematical formula for this, which you should not try to learn, I don't know it, and you should not really care about it, is this one. Yes, it's very scary. That's why you shouldn't learn it. And also, there's no use trying to learn it. There's nothing you can do with it. The only reason I'm displaying it is to tell you, to show you that it includes these 2 symbols, which should now be familiar to you. It's no coincidence that these symbols are there. This particular curve is the one that we obtain for the values of mu equals 0 and sigma equals 1. And if you recall from our indices of central tendency and dispersion, we use this letter to refer to the mean of a population, and this letter for referring to the standard deviation of a population. So what this curve can represent is probabilities or proportions that relate to a set of measurements, a population of values that has a mean of 0 and a standard deviation of 1. The reason we are so interested in this curve is that a lot of kinds of actual measurements we can make do have this shape or can be transformed to approximate this shape. And when you have real data and you plot their histogram, and the histogram looks like this, then this means that you can use your knowledge of the probabilities from the normal distribution to make inferences about proportions in your population of measurements. Let's make this a little bit more concrete. Think of this axis as number of standard deviations away from the mean. So 0 is 0 standard deviations away from the mean. So is the mean. Okay, if you're 0 away from the mean, you are the mean. So this is the mean right here. 1 means 1 standard deviation above the mean. -1 means 1 standard deviation below the mean. 2 means 2 standard deviations above the mean. -2 means -2 standard deviations below the mean. Therefore, if we apply the numbers we mentioned before to the situation where this is not a mathematical abstraction, but the histogram of an actual population of lots and lots of observations, then this means that we can reasonably expect, in fact, it has to be the case, that 68% of our observations will lie within 1 standard deviation away from the mean. So between -1 and 1. Let me say this again. In a variable that is approximately normally distributed, about 68% of the data will be within 1 standard deviation from the mean. This means that about 32% of the data will be outside. This means they will be farther from the mean than 1 standard deviation. So now you may begin to understand why we care about calculating a standard deviation when I said in talking about indices of dispersion that we prefer to use the standard deviation when we can, instead of the other possible indices of dispersion, and especially instead of the mean absolute difference, which seem to be pretty similar superficially. So the reason is, if you use the standard deviation, then you can know a lot about proportions of your data that are expected to be within or outside any given range. So if your variable is approximately normally distributed, about 1/3 or 32% of your data will be farther from the mean than 1 standard deviation. So what is the standard deviation then? It's the distance from the mean that contains about 2/3 of your data. That's why the standard deviation is so important. It's the range within which you find about 68% of your data. And that doesn't depend on anything about the nature of your data, about the mean, or about the standard deviation itself. It only depends on the measurements being normally distributed. It only depends on their histogram looking like this. If it does, then you know that 68% of your data will be within 1 standard deviation away from the mean. And therefore, if you apply the other numbers, 95% of your data will be within 2 standard deviations from the mean. So no farther than 2 standard deviations away. Between -2 and 2 standard deviations away from the mean, you have 95% of the data. And this means that 5% of the data are expected to be farther than 2 standard deviations away from the mean. So these proportions, these numbers that you have to learn, are so general that you can use them in very, very many situations, as we'll see later in the course. And that's why they're important to know. So whenever you can reasonably justify calculation of a mean and a standard deviation, whenever your data are approximately normally distributed, there is an intimate, mathematically based connection between standard deviations and proportions. So 68% of your data are within 1 standard deviation away from the mean, and 32% are outside, are farther from the mean than 1 standard deviation. 95% of the data are within 2 standard deviations from the mean, and 5% are farther than that. And 99% of your data are going to be within 2.5 standard deviations away from the mean, and 1% of the data will be farther than 2.5 standard deviations away from the mean. And you can find and see, you can find the values and see the areas that correspond to proportions for any number of standard deviations using the application online you can find at this link. And when it comes to a sample, instead of having the whole population, well, we just change the symbol and we can still reason in the same way. So if you're talking about a sample of data that you have collected, and this sample is normally distributed, then 68% of your measurements can be expected to be within 1 sample standard deviation. So the standard deviation of your sample, 68% will be within 1 standard deviation, 32% will be beyond, 95% within 2 standard deviations, and so on. So this is also true of samples. It's true of any set of values that are approximately normally distributed. And that's why the normal distribution is so important.